So let's take a look at Chapter 7, which is going to look at statistical significance, effect size, and confidence intervals. So we're going to roll it back. Populations, whole group, samples, subgroup of the population. Descriptive statistics, when I describe. Inferential statistics, when I want to actually make a conclusion, a decision, or an inference about a population. So when I'm making these inferences, you can even call them maybe generalizations. That might be a way to think about it. From a sample to a population, there's always the possibility that the sample does not represent the population. Even if you use random sampling, it's possible that in that random sampling, you chose the outlier people. So this is where the idea of chance and probability come into play, because we don't operate in a vacuum in the real world. So we can't be completely sure of everything. So we're going to define chance as the probability of an event occurring due to variations in the characteristics. Error is going to be known as a random sampling error. Notice this is going back to sampling again. This refers to the difference between the sample characteristics and that of the population that are caused by random changes, fluctuations in unpredictable items that are involved when selecting that random sample from a population. So with that, statistical significance has a lot of meanings to it. So something could be significant to you. You could say, wow, the test average was a 71 in one sample and an 80 in another sample. That seems really significant, but that doesn't mean that it's statistically significant. So our perception of significance is very different from what is actually calculated here. So when I do this, the probability, or what we call the p-value that we've been using our tables for, that a statistic derived from a sample represents an actual genuine situation. In other words, the effect observed in the sample data is not due to a sampling error or chance. So when I'm statistically significant, I'm saying, hey, this is an actual difference. There's something different between the two groups. To determine this, we've got to compare the size of the effect and the measure of random sampling error, which is usually a measure of standard error from the previous chapter. Statistical significance means that when I'm selecting my sample, the sample is likely to differ a little bit due to the population, just from random sampling error. So a little bit. Results that happen to this that are due solely to that sampling error are not considered meaningful. So when I say it's statistically significant, if I made a mistake in how I sampled people, I can't say that's a statistically significant difference. Now you're going to say, Dr. Robinson, how do I know that? Because statisticians don't just look at numbers, they look at context. So when I get to the end of a study, I'm going to go back and look at all of my methods and validate them or criticize them and then make conclusions. So to consider a result meaningful, I must rule out the fact that something went wrong in the sampling step. To make this decision, I can use probability to inform my choice. So I can use my p-value to know how likely something happened in the sampling process. So if the probability of obtaining a result by chance is too large, so if I'm saying I'm really highly probable to get something that's due to chance, I can't rule out that in chance. And I just have to say, hey, this is a limitation of what I studied. Chance could play a role in this. So it's more about recognizing where errors could come from than saying, like, I'm wrong. So how does it work? I'm going to calculate the standard error. Seeing the theme here with standard error. That's going to tell us how much difference we should expect to see between the sample and the population due to just that sampling error. If the statistic is quite larger than the standard error, then it's probably not due to random sampling error, so it's probably significant. So you're going to take a look at both of those. If I'm doing a hypothesis test, which is inferential, then a hypothesis is trying to establish whether or not something can be accepted or rejected, or you could say failed to be rejected. The null hypothesis always suggests that there's no effect. So my default is that if I give a sample a new drug for cardiovascular health, that it's not going to change anything. That's my null hypothesis, is always that there's going to be no effect, which seems counterintuitive because often we're trying to prove something and we try to prove it using the null hypothesis, which is wrong. The alternate hypothesis is what you're claiming you want to see happen. So there's two examples. So the null could be that the mean of the sample is equal to the mean of the population. And then I can make two alternative hypotheses. If that's my null, I could say, well, they're not equal, or I could say it's less than. So that's what creates our two-tailed or one-tailed test. A two-tailed test is going to be equal or not equal, and a one-tailed test is going to be just less than or greater than. Hypothesis testing is not perfect. Before you say fail to reject or accept or reject, you have to cross all of your T's and dot all of your I's. So you've got to check the standard error. You've got to check your sampling methods. Is there anything that could have gone wrong in your sampling methods? Is there anything that you see in your methods that could have resulted in something different? Maybe it wasn't random, maybe it was convenience. Maybe your error is larger than 5%, which for most people, if it's a bigger than 5% chance that you're wrong, we don't want to gamble on it. When this happens, we consider type 1 and type 2 errors. In a type 1 error, we reject the null hypothesis when it's actually true. So one way that we keep this from happening is we give really conservative alpha levels like 0.01. So what does that mean? That means you are 99% confident and only 1% non-confident that what you're saying is true. And type 2 error is going to be failing to reject the hypothesis when it's actually false. And same thing, we can use a more liberal alpha level as 0.10. Maybe we're being too rigorous and we want to say that we're 90% confident, not 99% confident. The p-value is that value you're finding in the chart in the back of your book. And it's the probability that something's going to happen by chance. So it's what's the probability someone's going to score a 90 on a test. I could go in there, I could get my z-score, I could look up the z-score, and then I could tell you what the probability is based on the table. In a normal distribution, we have those t distributions, f distributions, and other distributions that can be used to calculate probability. This is not the only way to do it. You're going to see multiple ways to do it. When I'm looking at the p-value thing, though, it's really nice because if the p-value is less than 5%, then I consider it statistically significant, and that's super easy, right? It's not having to look at t distributions or f distributions or samples of samples of samples. It's just look at the p-value. If it's less than 0.05, then you know the result is significant. So this is the graphic that looks at a two-tailed test. That test we talked about where the mean is not equal, that would be what this looks like. And so notice you've got reject HO because that's going to be if my p-value is in those areas. Hypothesis testing has a lot of limitations. It's really designed to be a yes-no. It's not a why. It's not a why, it's not a how, it's a yes or no. So many questions can be much more complex than yes or no. So is the mean equal in both the sample and the population? That's a yes or no question. But how large is the effect? I can't answer that with yes or no. I have to answer that with a number. So that's why we say that it's really designed and should be treated as a yes or no situation. It's really influenced by sample size. Hypothesis tests can give you the complete wrong information if you are using too few people. So you don't ever want to use below 30 people or we're going to have a problem with the validity of your results. So if I'm looking at effect size, is this significant and practical significance? I can look at this problem. I can say that I have measures of statistical significance that rely on the error, and that the error, like we found out in the previous chapter, is really impacted by sample size because I divide by the square root of my sample size. So an example would be if I have a sample mean of 105 with a population mean of 100, then I have the standard deviation of 15 and I have sample sizes of 25 and 1600. right off the bat, there's a flag for me because I see 25 and 1600 and I think, what were you thinking and what were you doing? Because you weren't thinking or doing anything that's good. So if I look at what I have and I organize it by my sample, that is what I would see in my visual. So what's the cure for these ridiculous sample size differences? It's really the effect size. It's to deal with the sample size issue and how it affects statistically significant. I use what I call an effect size to give me, what is the statistical effect and how can I minimize my sample size. So it'll tell me if I'm looking for this level of significance, I should have this many people in my study. If I'm looking to have this much impact, this is how many people I should have in my study. It's calculated, again, by hand, but we're going to use Excel, essentially by removing the sample size from the standard error. So you're going to calculate it just like you do standard error, but you're not going to divide by the square root of the sample size. Effect sizes are giving us a practical significance. They are not statistically significant, but they are practical to us. So if I have an effect size less than 0.2, that's less than 20%, I would say it's pretty small. If I'm between 25 and 75%, moderately confident what's going on is right. If it's greater than 80%, then we are definitely really confident. Confidence intervals, we're going to be calculating in Excel, not by hand, but confidence intervals are another way of measuring practicality and effect size. So by using the probability, I can form a confidence interval and say, I'm fairly confident the mean of this population or sample is between this and this value. So I'm pretty sure that people take between, 28 and 35 minutes for a 30-minute lunch. So that is what we're really saying. Most of the time, the researchers are pretty clear on wanting a 95 or a 99% confidence interval. And so when we're finding those values that go in there, we do have to take that into account, that we want them to be pretty darn confident. So if I want to actually create a confidence interval, here's a problem. We've got a random sample of 1,000 men. We've measured their shoe size. We've got the mean of their shoe size. It's 10. Standard deviation is 2. The standard error that I'm going to calculate using the standard deviation and the sample size, taking the square root, dividing them up, is 0.06. So how can I get a 95 confidence interval for what the mean is between in this population? So first I'm going to go to Appendix B. I'm going to say, okay, well, I'm doing a two-tailed test. My degrees of freedom would be infinite because there's 1,000 men here. My alpha level is 0.05, which is 5%, meaning I'll be 95% confident. And in that chart, I'm going to look that up, and my t-value is 1.96 for that. So then I'm just going to plug in the formula. My mean is 10, so it's going to be 10 plus or minus the t-value I found in the appendix times that standard error for the mean. And so when I do that, I'm going to say I am 95% confident that the interval of 9.88 and 10.12 contains the mean. Conversely, you could say I'm 95% confident that the mean is between 9.88 and 10.12. So two different ways to think of the same thing. So in conclusion, we've had a lot going on here about statistical significance. It's pretty fast-paced. Refer back to the confidence interval question as we calculate it, but really make sure you have access to those appendix tables because you are going to be using them quite a lot. So this is a summary of what we've gone over today. You can pause this, take a minute to read over it. But remember, when you're doing your ALA, it's more about putting those numbers into context than crunching those numbers yourself.